Okay, so let's get back to our discussion for today. Okay, so far so good. So I hope yung mga previous discussion natin about radio access network is not so deep, not ocean deep. And I hope no yung ating the way nung pag-deliver ko sa inyo ng information about radio access network, how the different portions or different equipment used in the radio access network, and then what are the different generations are clear, and it's easy for you to understand. So because naggano tayo ng oras doon kasi we need to establish yung ating foundation about the radio access network. So I want as much as possible everybody understand what is radio access network before we proceed to the Open RAN. Okay. Now the next topic is about 5G. Why we are talking about 5G in a separate topic? Because 5G would be one of the technologies that will be maximizing the capacity of it using the Open RAN system. Okay, so why is it like that? When we talk about 5G, so what is 5G? So 5G is the 5th generation of wireless technology that will provide wireless connectivity for everything. It is not like the 2G, 3G, or 4G, which is service specific. Like for example, for 2G, previously it was mainly designed for voice communications, right? Mobile voice communications. And then later on, nung deploy nila, ang nagiging killer application was the SMS. Okay? And then next was the 3G, which is designed for video call previously. Yun ang pinaka gusto nila maging killer application, but due to the booming ng smartphones, yan, so naging mas killer application yung mga accessing sa internet. Okay. And same with LTE and now with 5G. So 5G has a lot of applications right now and the use cases which we will be discussed later. So it has a faster than the existing mobile connectivity. So it compared to LTE, and lower latency, lower energy consumption. So lower latency means around 1 millisecond in the initial standards or initial target, and lower energy consumption up to 10 years. No, ayan yung pinaka target nila. And greater capacity. So in terms of the capacity, up to 1 million connected devices, no, per square kilometer. And then 5G has the potential to enable the new use cases and new applications for different industries, like what we call the verticals. And 5G requires defining a flexible architecture. So 5G will be utilizing this flexible architecture aligned with the needs from customer and business perspective. So 5G has these 3 use cases, what we call the enhanced mobile broadband, okay, the massive machine type communications, and the ultra reliable and low latency communications. And these use cases requires different parameters or different architectures. So that's why a flexible architecture is needed or needs to be aligned when we deploy 5G. And Open RAN is one of those key na para ma-implement natin itong flexibility pagdating sa 5G. So let's take a look at the 5G performance target in terms of these 3 use cases. So we have this in the EMBB, like for example, the initial target under IMT 2020 is 20 gigabit per second in terms of the peak data rate and 100 Mbps whenever needed. And in terms of the speed, is up to 500 kilometers per hour in terms of the mobility. So meaning, yung mga vehicles moving at this rate, we can still serve like airplanes and like bullet trains. Okay. In terms of latency or the instant response of the network, the target is 1 millisecond. Okay. And in terms of connectivity, how much devices are be able to be connected in this certain square area or certain area, it's around 1 million devices per square kilometer. And then in terms of energy efficiency, 100 times, and area capacity, or area traffic capacity is 10 Mbps. So 5G will have 20 times the LTE capacity, 10 times the user experience rate, and in terms of the air interface delay, it will have milliseconds rate. So this is coming from the ITU reference and 3GPP references. So what are the different aspects that we need to consider in 5G, or we need to know? So as mentioned, there is the three use cases, the major three use cases, the EMBB, which is data rate and capacity. So when we say EMBB, enhanced mobile broadband, we only mean higher capacity and higher data rate. Okay. URLLC is for the latency and mobility, meaning instant response ng network. Okay, up to 1 millisecond. Connection density, MMTC, the massive machine type communications, which we also call the massive Internet of Things or IoT, up to 1 million devices per square kilometer. And 5G also uses different bands. So we have what we call the sub-6, and we have the super 6 gigahertz. No? So in simple terms, we call it the FR1, the frequency range 1, and the frequency range 2. Or you will also hear the what we call the millimeter wave. So these are the millimeter waves. And then these are the sub-6 gigahertz. And 5G also, in terms of the licensing, we can also use the licensed frequencies. And in case of the US, the CBRS, they have what they call the unlicensed or the shared license or license shared frequencies. And we also have the unlicensed band, specifically for 5 gigahertz band, in which also used in the Wi-Fi. 5G also have this millimeter wave and the massive MIMO applications. Flexible numerology. So what is the flexible numerology? Previously, the LTE, the subcarrier frequency of the LTE is only 15 kilohertz. Ganito siya kanipis. No? And due to the requirements to become the need to become flexible in terms of the network architecture or the network deployment, we also want to have flexibility in terms of the frequency use. Okay? Because last time when we deploy 2G, 200 kilohertz only, naka-fix tayo doon, and then suddenly we have 5 megahertz, and then for the LTE, we have a different flexible frequencies, no? We have the 1.4, 3 megahertz, 5 megahertz, 10, 15, up to 20, and then carrier aggregation. Now, inside those frequencies, there is a fixed subcarrier spacing, which is 15 kilohertz. That is the numerology, 0. In 5G, they introduce a flexible numerology, meaning, for example, in a 20 megahertz, in LTE, there is 15 kilohertz, right? When we say flexible numerology, what 5G will do is that from the 15 kilohertz, you can change it to 30, to 60, to 120, to 240. That is how 5G is flexible in terms of those subcarrier. Why is it like that? So this is to address the different requirements, like for example, EMBB, URLLC, and MMTC. Okay, that's why there is a flexible numerology. Next is the CP, the control plane, and the user plane split. So they split the control plane and the user plane. And then it also introduced the slicing, the network slicing. So this is a virtual slicing of the network. Like for example, all EMBB is utilizing same resources or different resources compared with the URLLC. So they are not mixed inside the core network. They are separated virtually in terms of the network slicing. And there is also the CRAN, the centralized RAN application, in which the BBU resources are pooled. Okay. Next is unlicensed and the satellite access. Okay, so there is an unlicensed using the 5 gigahertz frequencies and the satellite access. You will hear it also already, no? There's like for example, yung mga satellite internet provided by Starlink and the OneWeb. So they are now trying to explore the the non-terrestrial implementation in terms of the 5G, the NTN. And then we also have what we call the D2D or the V2X. D2D means device-to-device communication. And it is also implemented in the V2X system, the vehicle to everything. It is where the machines or the vehicles are empowered with intelligence and connectivity to the internet. So that is V2X. And there is a different link right now because previously we have what we call the uplink, mobile to the cell site. That is the uplink, and the cell site going to your mobile is the downlink. Now, if you have two devices connecting to each other, we call it the D2D, device-to-device communication, the PCI 5 link. Okay, we call it actually the side link, side to side. And then we have this LTE and NR integration options, in which we could have the implementation of LTE as a master node and 5G as secondary node. This is what we applied in the Philippines, the NSA approach, the non-standalone approach, in which your mobile phone is connected into two different networks, LTE and 5G. So that is the non-standalone approach. And also we have the SON, the self-optimizing or organizing network, the software-defined network, and network function virtualization, in which all the functionality, like for example, the BBU are now virtualized. You can install it in a COTS hardware, so you can have creation, deletion of particular task or procedure coming from this BBU. So this is how the 5G will become flexible in terms of the implementation. You can create, delete anytime, or in the cases where you need to have another applications to be created sa network mo. Yan, so ito yung mga NFV natin. Okay. Meron pa ba? Yan, wala na, no? So, and then we have this 5G spectrum and services techniques. So 5G is the only technology that can handle a wide range of frequencies. Like for example, from 300 megahertz up to 90 gigahertz. So si 5G pa lang yan. Because our 2G is operating at 900 and 1800 megahertz. For the 3G, we are operating at 450, 850, 2100, and 3500. There is no millimeter wave in 3G, and the same as LTE. LTE is up to 3500 also. But in 5G, we have this what we call the millimeter wave. So it starts from 24 to 39 gigahertz. Okay. And then massive MIMO is become the what we call the default implementation in 5G. So it uses a beamforming that can increase the spectral efficiency and network coverage substantially. So beamforming is more practical at higher frequencies because you are considering the size of your antenna and the number of elements. If you use the beamforming into lower frequencies, particularly like for example 700 megahertz, your antenna size will become huge. No? It is not practical. It can be done, but it's not practical in terms of engineering. What else? So massive MIMO will be part of the 5G specifications and deployment from the day one. So it will become like a default configuration of a 5G. Just to maximize, of course, the capacity or the potential of your network. If you're not using 5G massive MIMO, it's just like you buy a car, like for example, a Ferrari, and then you drive it only on the streets. You cannot maximize it. You just have to lay down some big road for you to maximize your Ferrari. Okay, and then we have what we call the network slicing, as I mentioned. Okay, so network slicing is so there's a physical and protocol layers in 5G need to be flexible in the design and to order to support different use cases. Okay, so different frequency bands and to maximize the energy and spectral efficiency. So the network slicing will create a virtual network segments, okay, for different services within the same 5G network. Okay, so the slicing capability will allow the operators to support the different use cases and enterprise customers without having to build a dedicated network. Okay. So like, for example, if you want to deploy 5G in your factory, no need to build a new network there. No? So just buy a slice to the operator. So the operator will give you a dedicated slice. So meaning that dedicated slice will not be shared to the public. So your company or your factory will only is the sole user of that slice. So you're not mixed with the public users. So that's one of the applications of the network slicing. This one I mentioned already, dual connectivity. So your phone is connected via LTE and via 5G if you're using the NSA, the non-standalone mode. So if you have this 5G phone and then you see a 5G signal in your phone, meaning your phone is connected to LTE and 5G at the same time. Okay, so that is what our network is being set up. Okay. What happened to WiMAX? It was used before by Telco, Y-Tribe, if I remember it correctly, to provide 4G access. Probably the business case is not, first is the business case, and then worldwide it was not that successful to be adopted by every operator. Okay, so because WiMAX is not part of the 3GPP, it's a different road or different path, no, different specification. So mas naging boom yung LTE compared kay WiMAX. Okay. Last is the cloud optimized architecture. Okay, so it supports for cloud implementation and edge computing. So the current architecture in LTE network is fully distributed. Okay, and the radio and fully centralized in the core network. So sometimes there are applications that requires low latency, and the content you want to bring the users close to the radio. So it leads to the local breakout and edge computing. So the scalability requires the cloud benefits to be brought to the radio networks and with the cloud edge architecture. So 5G radio and core networks are specified for native cloud implementation, including new interfaces inside the radio or inside the radio network. So you will hear here the cloudification, network function, virtualization, containerization. So this is just to optimize the architecture of the 5G. Okay. When we look at the standardization of 5G roadmap, so here it is. So we started as release 15. Release 15 is the 5G first release, the phase 1. So it was freeze last June 2019, and then most immediate needs is for EMBB, initial URLC, and the frequency is below 52.5 gigahertz. So the release 14 is the initial studies. So this is around the LTE Advanced Pro, and then 5G phase 1, and then release 16 is 5G phase 2, and then release 17 is freeze last July 2020. So there is an improvement, okay, like a NTA, higher frequency, and integrated access backhaul. And right now, there is a significant step forward for EMBB versus the non-EMBB and then cross-functional. We call it the release 18. So the release 18 is also called the 5G Advance. So whenever you hear a 5G Advance, it is in the release 18. But what is the release 18? No? Release 18, 17, 16, 15, and 14. So this is defined by the 3GPP standard. Okay. So 3GPP means third generation partnership project. So this is a union of 7 telecommunications standard development organization. Okay, so they provide their members with a stable environment to produce the reports and specifications. So basically anything that is 2G, 3G, 4G, 5G, 3GPP standard, it will be applied across any countries that are adopting this 3GPP standard. So whenever you go from the Philippines, going to, like, for example, US, Japan, Korea, Singapore, if they are using a 5G based 3GPP, you are assured that your phone will work, and then your knowledge about the 5G is almost the same because you have the same standard, because it's applicable in every part of the world. Okay. So when you look at the 3GPP standard, this is it. This is their website. Okay, so when you go to 3gpp.org, okay, so let me share the link. Okay, so the link is here, 3GPP. Okay, so as part of our exercise, we will save it to our folder. Okay, so 3GPP, if you want to review the specifications, so like for example, you're in the operator or you're in a vendor or equipment manufacturer, you can go to the different releases. Okay, so release 99 is a 3G. Okay, release 4, HSDPA, up to release 8. Release 8 is the LTE, and release 15 is the 5G. Now we are on the release 18. So let's take a look on the release 18, what they are doing in the release 18. Okay. So in the release 18, so these are the topics that so you can find all the standards and specifications and guidelines for from 2G up to 5G. So if you want to learn more deep on the parameters, deployment options on the 5G, you'll just go into this website, download the specifications or standards, and then you can just read it and study it. Okay, so that is the 3GPP. Now let's take a look at the 5G system. So the 5G system, also known as the 5GS, so it is composed of the 5G core network, a 5GCN, and then it is connected to the 5G access network, and the 5G access network can be separated into two. It's a 3GPP, next generation radio access network, or NGRAN, or a non-3GPP access network. Yeah. So the standard, the NGRAN can be a standalone new radio base station, a standalone long-term evolution. So you can connect an LTE, just upgrade it via software. You can connect it to the core network. A non-standalone base station using NR, a non-standalone base station using LTE as the anchor, and NR as an extension. Later on, we will check the different deployment options. You can also connect a wireless local area network, or WLAN, based on a Wi-Fi and non-3GPP interworking functions to the core network of 5G. So that's how flexible yung ating 5G core network. So you can connect either a 3GPP next generation radio access network or a non-3GPP access network. And then it will be connected to the user equipment. Okay? So this how flat or straightforward the architecture of a 5G system. Core network, access network, and then the UE. Next, we'll review the control plane and the user plane. Okay, before we go to the architecture of the 3G. So the control plane and the user plane. Just imagine like this, no? If you want to get money from the bank, so whenever you want to get money from the bank, there's two ways. There are two ways, no? So one way is to rob it, and number two is to have a withdrawal. Okay, withdraw. Just get withdraw. Let's go to the option of withdrawal. So when you want to withdraw money from the bank, so you need to go to certain processes or procedures. First, you need to show to the bank teller, or you have to queue first. You have to queue, and then you have to wait for your turn, and then show your what do you call this card? Anong tawag natin doon? Bank card ba yun? Passbook, bank book, no? You want to show the bank book to the teller, and then want to verify what's your name, what is your account number, and then how much money do you have in the bank. So and then after that, how much money you would like to withdraw. So that procedure is what we call the control plane. So it carries the signaling traffic. And then once you satisfy all those procedures under the control plane, it's time for the control plane to allow the user plane, the user plane to give you the data coming from the core or the server going down to your UE. So it's just like they will open the vault, get the money, count the money, what you would like to withdraw. And then if you satisfy all the requirements, you have this amount, you have this money in your account. And then what you would like to withdraw is lesser than the money that you have. So it's so you will be allowed to get this amount to be withdrawn, and then the teller will give you the money. So that's how the user plane and the control plane is separated. So in 5G it was separated. Okay, the user plane, okay, the user plane or the data plane is where most of the data transforms happen. So the data plane or the user plane is optimized for speed of processing, for simplicity and regularity. And then while the control plane, okay, it controls the data plane. And it is optimized for decision making and in general facilitating and simplifying the data plane processing. Okay. So sometimes the data plane or the user plane is also known as the forwarding plane, carrier plane, or the bearer plane. Okay. So basically it carries the network user traffic, and the control plane carries the signaling traffic. Okay. So when you look at the architecture of a 5G network, it looks like this. So it is separated into two: control plane and the user plane. Okay. So you can see these colors. These are the control plane, and these are the path for the user plane data. So specifically, there's a data network, and then there is a network function that is handling the flow of traffic from data network going to your access network and going to your equipment. So if, for example, you want to download something from a certain website, so the user plane is there to control the flow of traffic. So let's take a look what are the different elements of this one. First in the list is the access mobility management function, or the AMF. So the prime responsibility of this function is to allow the UE to register and then register with the 5G system. So it's just like creating a bank book, a passbook in the bank. So the registration management is here, connection management is here, reachability management, and then the mobility management. Okay. So next is the session management function. So it's a control plane. Okay, this one. Control plane that includes the setup, modification, and release of the packet data unit session. Like for example, in the 4G, the session, we call it the EPS, bearer session. But in 5G, we call it the PDU session. So it's a different terminology, but almost same concept. Okay. So in the session management function, or the SMF, okay, so this is where the IP address allocation is happening. So this is the one that giving you the IP address. So the IP address session transfer is either IPv4, IPv6, or an Ethernet or unstructured data types. And then we go to the user plane function. Okay, so the user plane function is responsible for routing and forwarding of user plane packets, the base station, and the external data network. Okay. So it is also responsible for enforcing, like for example, if you're familiar with a core network, the session aggregate maximum bitrate bitrate. So which defines the maximum permitted bitrate summed across all the non-GBR, for example, the QoS flows belonging to a specific PDU session. What do I mean by this is that, for example, you have a very, very good signal. Okay, you have, for example, neg 75, and then signal to noise ratio is 20 dB SINR, and then you have big data, no? Like for example, you have 40 gig in your account. Whenever you try to do download, the UBR or the AMBR, the session aggregate maximum bitrate, will limit you. So there is a parameter in the core network that will limit your download speed. So even though your system or your radio access network can give you around 1 gigabit per second, if the AMBR is not allowing you to have that kind of throughput, you will not get that one unless you change it. So this is where we set it up in the UPF. Okay. And then other functions like, for example, the authentication server functions. Okay. This is to support for both subscriber and network authentication. Okay. And the unified data management function, the UDM. Okay. So similar to home subscriber server or the HLR within the 4G evolved packet core and the 2G and 3G. So this is where the subscriber information is stored. The other functions we will not discuss, but we will go here. The network slice selection function. So then the network slice selection function, this is where giving you the specific slice. So identifying. So whenever you connect to the 5G core network or 5G network, you have this what we call the NSSAI. So the network slice selection assistance information. So it tells to the core network which slice of the network are you accessing. So is it the EMBB? Is it the URLLC? Or is it the MMTC? So in this case, once the NSSF identified your network slice identifier, it will allow you to access that kind of slice. Okay, so you are not bombarded inside the core network. So as I mentioned, there is a network slicing procedure inside the 5G core network. Okay? Bakit pa minsan malakas ang signal bar pero mahina ang data? That is based from the number of subscribers in the area. Just like Joy, when you try to have mag-shower ka early in the morning, but probably 7 or 6 to 7, and then maraming nag-shower din within your village. So although malaki yung tubo mo, that is your signal, but the droplets of shower is not that malakas kasi ang dami yung naliligo. So most of the time, it's a concentration of the number of subscribers inside the area. Kahit malakas yung signal mo, pero kung marami kayo naghahati sa resources, it will affect your data throughput. Okay? Yan. Mas maligo na maaga. Okay, so this is the 5G core network. So when you look at the LTE core network, it looks like this. Okay, so you have the base station. For example, this is a massive MIMO, and then you have this BBU. So normally, the user plane is connected to the MME, the mobility management entity, and the control plane is in MME, and the user plane is in the SGW, serving gateway, going to the internet. Okay, so there's a policy control function, and then the PGW. When you simplify the 5G architecture, it looks like this. Your base station is connected in the control plane to the AMF, okay, access and mobility management function, okay, and the UPF, user plane function, okay. So it's logical to say that the MME is equivalent to AMF, and your SGW will be equivalent to the UPF when you compare the functionality of LTE and 5G. Okay. Okay. What else? So we have two major network architectures in 5G. Okay. So first is the non-standalone mode. Okay. So the non-standalone mode, or the NSA. So it is where you are using, okay, the core of LTE, and the master node will be the LTE, and the secondary node will be the 5G. So there is a connection, X2 interface between the E node B and the ENG node B. So when we say ENG node B is EU-TRAN NR G node B, no? Okay. So you have a connection to the EPC. But this architecture only supports EMBB. And it's reusing the EPC and LTE as an anchor and dual connection for user data. This architecture is the one that initially implemented here in the Philippines and in other countries as well. So the option 3. So this is the fastest way to implement 5G. And then our holy grail for 5G is the option 2, in which the core network is in place. And directly connected to the 5G core network is the G node B. Okay, G node B. And we call it the standalone mode. So in the standalone mode, it supports the end-to-end network slicing and the 3 use cases of 5G: EMBB, URLLC, and MMTC, because that is because of the help of the 5G core network. But the downside is you need to have a good 5G coverage area. So some of the operators in abroad, they are going straight into SA, specifically for those new players. No? But in the Philippines, we are going for a transition. Like, for example, option 3 going to option 2. So there's a different steps going to option 2. Okay. Okay. So there's a lot of options in deploying 5G. So if you want to go for 5G deployment options, we have the option 2, okay, option 5, option 3, option 3A, option 3X, 4, 7, 7A, and 7X. Okay, so probably in a separate session in Asia Open RAN Academy, we'll have a 5G system topic. So mostly we will be discussing all of these 5G options there. Okay, and then we'll go straight to the RU CU-DU split in 5G. Okay, so this one is really important also. So when we first implement the 4G in the network, we have this kind of architecture. You have the core network, 4G and 5G, and then the BBU, RRU is the RAN, and then it's connected by a backhaul. And the connection between the BBU and the RU is called front haul. Okay, front haul. Under the 3GPP approach, in the technical reference 38.801, the CU-DU split is being introduced. Okay, so the BBU is now separated into 2 functions. So if you have a 5G core network, so the BBU is separated into CU and the DU. So CU is centralized unit. So it runs the RRC and the PDCP layer. Okay, so remember the protocol layers, right, of 5G. So you have the RRC and the PDCP layer. The G node B consists of probably a CU and 1 DU connected. And the DU is what we call the distributed unit or the distributed unit. This sits close to the RU and runs the RLC, MAC, and the higher physical layer. Okay, so depending on the split. Okay, and the RU is the radio unit that handles the digital front end and the parts of the physical layer, as well as the digital beamforming functionality, for example, the massive MIMO. And 5G RU designs are supposed to be inherently intelligent. No? But the key considerations of RU designs are, for example, you want to have a remote radio unit that is smaller, no? Lighter, so that the tower loading could be maximized and the power consumption. So you want to save OPEX for the power consumption. Okay, so this is what happens in the RCU-DU split. CU-DU split. So take a look at the implementation. Okay. Okay. So if the architecture is separated, is disaggregated like this, so you can implement a 5G network that is flexible based on the applications that you want to implement in your network. Okay, so there are applications like, for example, you want to implement, you want to put, basically the RUs are located in the cell sites. Okay, and then the DU could be located probably inside the cell site if you are requiring higher latency, or you can put it in a data center where it is connected also with the CU, which is located in the regional area. And so you can be connected in the regional area before the core network. So it's one way of the centralization of your implementation. Okay, so it is important to note that the DU-CU split is hardly impacted by the type of infrastructure. Okay. Now we will have a new interface here. So you have the front hole, and then you have the back hole. In the middle of the DU and the CU is the mid hole. Okay, so there is a new interface here. So we have this, what we call the F1. Okay, so which with the increase of the deployment footprint, fiber and availability of required front holes can be challenging. So because sometimes there's a lot of data you need to transmit going to the RU. So the front holes is becoming more challenging. So by distributing the protocol stacks between the different components, like for different split solution providers can focus on addressing the tight requirements of a near perfect front hole between the RU, DU, and the CU. So how do we split the functionality or the protocols? So remember the the different protocols that we have studied earlier. So the choice of how to split the new radio functions in the architecture depends on some factors related to the radio deployment scenarios, constraints, and intended supported cases. So we have 3GPP defined 8 options, functional split options for 5G. So we have the option 1, option 2, option 3, option 4, 5, 6, 7, and 8. So if you split your network into option 1, meaning in the CU, it only handles the RRC protocol. If you go for the split in option 2, meaning your CU is handling this one. Okay, option split 2. So the PDCP is handled in one box, PDCP and RRC. And the remaining could be the DU, high RLC, low MAC, high MAC, low MAC, physical, and low physical, and the RF is in one box. Okay. There are 3 keys why we are implementing this. So number 1 is the need to support the specific QoS requirement per offered services. Like for example, if you want to have a low latency, high throughput for urban areas or non-real-time applications. And the next is support for specific user density. So if there's a lot of users in the area and there's a lot of load demands per given geographic area, so we need to choose a right functional split. And of course, the available transport networks with different performance levels from ideal to non-ideal. Okay, so let's see what will happen if we do the different splitting. Okay, under the 3GPP, for Open RAN, the split that they are proposing is the split 2. Okay, the split 2, the 7.2. Okay, not split 2, no, 7.2 split in terms of the RAN. Split 2 will happen in the centralized unit. Okay, so these are the different protocols: RRC, SDA, PDCP, RLC, MAC, and physical. So the RLC have high RLC and low RLC. The MAC are the high and low MAC, And the physical, we have the high physical and the low physical. So under the high physical layer, you have the forward erection error control, correction, scrambling, modulation, layer mapping, and the lower physical is the beamforming, inverse fast Fourier transform, and the resource mapping. So sometimes we are splitting it now in some of the applications. So split 8 is here, and then split 7.2 is here, split 6 is here. So the SCF is implementing this. But in the Open RAN, we are they are proposing this split 7.2. Okay. So let's see, what will be the impact, Like for example, when we look at the split 7, okay, so this is a good example coming from parallel wireless. So on the right side, you can see the core network. So this is the core network. Okay. Now, if we are going to apply for a split 7.2, the RRU functionality, okay, the RRU will carry the RF and the lower physical layer. Okay. So this includes the IFFT, fast Fourier transform, the cyclic prefix. Okay. Now in the DU and the CU, they combine it into one box, which handles the higher physical layer, the MAC, the RLC, and the PDCP and RRC. So this is applicable, this scenario, the split 7.2 is applicable for urban areas. Okay. So where we kept the RF and the low physical layer at the RRU, and deployment of 4G solutions. And deployment is based on the morphology and availability of front hole. Because this one would be handling the open front hole when we use the Open RAN. Okay. Now the split 8 looks like this. The split 8, only the RF is here. Okay, only the RF is here. And the physical layer, the higher and the lower physical layer is in the DUCU. So what will happen is we simplify. Okay. So it will have a more energy efficient radio resource because the complexity design of your RRU will be more simple or simpler. Okay, because it's only when you design the circuitry of this, it only contains amplifiers, RF front end, so it will be more simple. Okay, compared to the split 7.2, which handles complex tasks in the RRU. Okay, so that's how the flexibility in the architecture is being done in terms of the hardware. So when you compare it like this, okay, you will see here that the different split options have a different uses. Okay, like for example, the split 8, okay, where the RF is being handled only being implemented only in the RRU. So the RRU will become simpler in terms of the circuit design, and the transmission between the RF going to the CUDU will require less bandwidth. So this option or split option is ideal for 2G and 3G. Okay, in terms of improved performance and throughput. Now, in terms of application for 4G and 5G, the 7.2 split is recommended by 3GPP. So what is happening here? The lower physical layer, okay, so that includes the beamforming, okay, will be embedded here in the RRU. So when you implement the massive MIMO, so it will be like, for example, if you have an antenna with integrated RRU, which is the massive, the AAU. So the complexity of your RRU can handle these requirements. Okay, so that's why it's in the 7.2. So you can implement it in the 4G or 5G. Now, if there are applications like, for example, your delay is not so sensitive, like for example 1 to 10 milliseconds delay, you can choose the split 2. Okay, split 2. But in terms of the performance, it's only for when you compare it to the 370 Mbps, it's only have 410 Mbps compared with this split 7. That's why also in the Open RAN network, split 7.2 is the most optimal split that we can use when we apply Open RAN in 5G. So we can maximize the performance of our network.